Hello everyone, as Ms. Graves said, my name is Gabriel Bell, and thank you for coming to my presentation today on the application of Python in modeling physics. And thank you, Ms. Graves, for facilitating this passion of mine. This is a project which frankly has taken up a good portion of my mind for almost a year now, and effectively defined my high school career. And so for that reason, I appreciate the opportunity to share that with everyone here. Like with all stories, the best place to begin is the beginning, the very beginning, the exigence behind my project. And that starts in the year 1977. Star Wars is released in America and becomes an instant phenomenon, capturing the minds of kids and adults alike, driving the resurgence of the science fiction and space opera craze, and shaping how stories in space would be told for the foreseeable future. A couple decades pass, 29 years to be exact, and they release just a few more movies, cementing Star Wars as a franchise and staple in pop culture rather than just a passing craze. And finally, the next year in Virginia Beach, 2006, Gabriel Waters Bell is born. I kid around for a couple years, but eventually in 2010, I decided to suddenly lock in and gain consciousness and start forming memories. Around this time, I watched Toy Story 2, the main villain of which was Zurg, and it's revealed towards the end of the movie, in, might I say, a very dramatic scene, that he's actually the father of Buzz Lightyear. This reveal naturally blew baby Gabriel's mind, to which his parents said, well, if you think that's cool, you should watch this. To which his mind was promptly blown 6 more times consecutively as he watched the entire Star Wars saga. And from this moment on, his fascination with science fiction, and science in general for that matter, was firmly cemented as the primary interest in his life, which defined everything from what he wore to what he studied in school, the effects of which I'm sure we'll see materialize soon enough. Over the next many years, my interest in science grew, and as I grew up, I wanted to know more about how all this sci-fi nonsense worked. To which I was met, of course, with the disappointing realization that, quite frankly, it didn't. But by this point, I was well grown enough to not care, and instead decided to continue pursuing my interests, learning a love for understanding how the world works. It was through my junior year physics class with Mr. Eisel, I learned that what had really fascinated me all those years was physics. I have to also give credit to a certain podcast, Science and Futurism with Isaac Arthur, president of the National Space Society. Where science and futurism fascinated me with the discussion about the miraculous world of high-energy physics, Mr. Eisel gave me an appreciation for the basics, the discipline of physics, and how to actually understand it on a conceptual level. And it was this which would go on to define my project. Sometime through junior year, I received an email about an opportunity to gain an internship at Jefferson Lab, a nuclear physics laboratory located right here in Newport News, Virginia. And I kept that email in my back pocket, knowing that it would eventually make a great senior project. Flash forward a handful of months, and I find myself at the senior project gallery. And to my good fortune, I found out someone in the class of 24 had done exactly that as their senior shadowing. Naturally intrigued, I asked them what advice they had for someone wanting to get into the same program. To which they recommended me to review your Python, make sure you understand the basics. They're gonna ask questions about that in your interview. And to which I replied, what? Leaving that night, I'll admit I was a little distraught. My only experience in computer science in general, let alone Python, was a 6th grade coding class where we did homework half the time and played Minecraft the other half the time. Suffice it to say, the only lasting impact that class had on me was the book I borrowed from my teacher and forgot to ever give back. Sorry, Miss Hendricks. For all intents and purposes, I had 0 coding background with which to go into this interview. And with the application due then in about 2 weeks' time, neither had I time to learn Python between now and then. The due date passed by, and I found myself once more struggling for ideas. So I asked Miss Graves. She said quite sensibly that if I didn't know Python, and it was obvious Python was going to be a skill I needed for a future in physics, then it would be a good idea to learn it. And hey, it might make a good senior project along the way. So that's what I did. A little unsure where it would lead me, but I knew we'd get there all the same. I had a goal, a clear goal. And if there's one thing I'm capable of, it's pursuing a clear goal. With the recommendation of Ms. Graves, I started in a program called Intro to Computer Science in Python with CodeHS. It was exactly what I needed, an overview of Python starting from the very beginning with Tracy the Turtle, who could be given simple commands using basic Python syntax and in turn trace out shapes and patterns on the screen to the script specifications. This ultimately wasn't very applicable to me in my project, but it was a necessary step in the learning process. Tracy served to show how Python reads and understands code, the importance of indentation, the order of operations Python follows, and the processes such as loops and logic, which we'll get into later. This carried me right up until and slightly into the summer of that year, by which point I decided my project was going to be creating scripts to model basic interactions in physics, the type you'd find in an AP Physics textbook, and then assess how accurate the simulation's predictions were by testing it in the lab. However, after finishing Code HS, I realized that my skills weren't nearly where I needed them to be in order to accomplish what I had set out to do. So once more, I went to Ms. Graves for help and received another simple but endlessly helpful recommendation. Udemy has some solid Python courses. And honestly, that was all I needed. I had another clear, pursuable goal ahead of me. Soon after, I was fortunate enough to catch Udemy at an 80% discount and picked up their top course for the low price of $30. The Complete Python Bootcamp from Zero to Hero with Jose Portillo. This course was where I truly found both a passion for Python and began to understand it on a conceptual level. Programming languages are conceptualized on a high level by what are called programming paradigms, ways of classifying languages by how they are organized, what grammar and syntax they use, the way they are read, interpreted, and execute lines of code. Python is an object-oriented language, which means that data and functions that are used to manipulate data are grouped into discrete units called objects and methods, respectively. Objects are grouped into classes, and each object has attributes, which tell Python what the object is, and methods, which tell Python what you can do with the object. Without going into excessive detail, which would take a course just like I did to understand with significant meaning, Python is characterized by these objects and the ways in which they interact with each other, and how Python interprets their attributes and methods. So to understand how to code in Python necessitates understanding these objects. In a similar way, I'd argue physics can be conceptualized. Just as an object in Python has attributes which constitute what it is, objects in space are characterized by their attributes like mass, charge, shape, position, and so on. Likewise, objects have methods as well, what you can do to them, such as accelerate them, charge them, induce a torque to cause them to spin, or anything else. That is all to say, I got down the basics. From Zero to Hero in Python was a much more complete package of everything I needed to know about the language. And with it, I began my project. At this stage in the game, I was more or less ready to start on my project. However, I needed a little more guidance. And thus began my collaboration with Mr. G, my, for the record, favorite teacher I've never had the pleasure of having as a teacher, trademark. With Mr. G, first we came up with the sorts of scenarios you might be able to model in Python, using the basic perspectives and units in AP Physics as a guideline: projectile motion, kinematics, work and energy, rotation, and crucially, movement on a ramp. For several weeks, I worked on coding these scenarios in Python, starting with a basic set of parameters and using those to graph the interaction over time. I did this chiefly with three problems, that being an object sliding down a ramp onto an infinite plane, an object rolling down a ramp, and linearizing with simple harmonic motion to find a spring constant. All problem setups that could easily be solved and understood by an AP Physics student. These for now were just a proof of concept. And with them done, after a few weeks of troubleshooting and applying the Python I learned, I reconvened with Mr. G. As mentioned, my original intention with the project was to test these scripts, see how accurate they were to reality. However, as I spoke with Mr. G leading up to the final time for the project, we realized that doing so was more or less an exercise in reinventing the wheel. We'd inevitably receive only the expected results, that yes, indeed, the laws of physics do still hold true, with any deviation due largely to experimental error. For this reason, we came up with a set of much more interesting driving questions for this product, that being regarding the problem-solving process in Python. One, how do you go about taking a problem in physics and converting it to Python? Two, why and when would you want to solve a problem in Python? Three, what limitations and benefits does Python have for solving problems in physics? To answer these questions, I tried my hand at being a teacher. I first recorded a video showing how to go about solving a problem like this, first going through it by hand as you'd solve it on paper, then doing the same process and translating it to a Python script, to both solve the problem but then also derive additional information from it, such as the path of the object, the displacement over time of the graph, and the displacement in any particular dimension as well, x or y. Following this, we arranged for me to present exactly this to Mr. G's AP Physics 2 classes during second and third block. As a matter of fact, I think I see several of those faces in the audience now, and I thank you for attending. But with Mr. G's classes, I had them first answer a 5-question pretest to assess their confidence with Python beforehand, and rank them based on agreement. They were therefore asked the following questions. 1, I believe that I could use Python in computer science to solve basic problems in physics and in everyday life. 2, I believe that if given a script in Python, I could accurately assess what the purpose of it is and roughly what it will do when run. 3, I believe that I could identify the types of logic and object types that are used in Python code and how each of them function and interact with other object types and logic structures. 4, Python has significant applications and utility in physics, both at a high school level and in higher education. And 5, I believe that if given a problem in physics, I could use Python to solve the problem and analyze the answer to provide a higher understanding than on paper. They were asked to rate their agreement on these questions on a scale of 1 to 5, from strongly disagree to strongly agree. The change in their answers from pre-test to post-test, shown on the graph here, was how I assessed the effectiveness of my presentation. As you can see, the blue indicates their answer beforehand, and the red the answer afterwards. In all cases, we received an increase of over 1 whole point in agreement. After their pre-assessment, we went about setting up and solving the problem, that of a box sliding down a ramp with a known mass, frictional coefficient, and angle. Following this process, as taught by my physics teacher, Mr. Eisel, we received an equation which you can see up here. And from this, we could simply plug in any number for time in this equation, t, and we get back the displacement down the ramp. Simple. However, then we went about taking this problem and converting it to a Python script, working in a code-along style where I asked the class to do this problem along with me using Google Colab. I explained first how to start a problem like this, importing the libraries you know you'll need, defining the variables necessary for the equation, such as your forces, mass, constant of gravity, and so on and so forth. Just like in any other problem, you can then use your equations of motion and Newton's laws to solve for your desired value, in this case, displacement. You can do it for just one number, or using the PyPot library, graph it over a time interval. However, things get a little more complicated when your ramp has a finite length. And after that point, you have to use loops and logic to continue calculating the motion of the object. Similarly, when solving the problem by hand, you have to divide it up into 2 parts. One part of the problem where your object is located on the ramp, and the other part where it is not on the ramp. In both cases, the general idea remains the same. I would like to, however, point out the key differences between these 2 approaches, Python and manual problem solving. For one, remember our equation from earlier that solved for displacement? Because this was solved in good solution form, trademark pending, we could see that our variable for mass m was nowhere in this equation, and therefore its displacement down the ramp in a given time was independent of mass. This fact was not as transparent in Python. Highlighting the limitation of that, Python, as an object-oriented language rather than symbolic, deals in data and numbers rather than symbols. And so, especially in larger scripts, these minute details such as mass independence are often lost in the coding. However, simultaneously, this shows the utility of Python as well. This graph here consists of 2,000 data points, which if we were doing so by hand would take an absurd amount of time to do. Python, however, can execute millions of cells in a fraction of a second if needed. And this point brings me to my main takeaways from my project. Python is a tool and aid, however, it is not a replacement for understanding. To code a script in Python requires an understanding of the underlying physics and vice versa. You cannot understand physics if you can't do it by hand. Take away the second. Python is a general use tool for solving problems, not just in physics, but in life as well. Just as you can use it to solve for displacement down a ramp, you can also use it to manage emails, automate responses, and come up with unique solutions to complicated issues. That is all to say, I don't think this skill is a one-time use, and frankly, I encourage everyone in this group to try their hand at it as well. It's fun. So now that brings me to my thanks and closing remarks, if you will. First and foremost, I'd like to thank Ms. Graves, of course. She said that the people we should be thanking are the ones who didn't have to help us, but who did. And while it may be Mr. Graves' job to make sure this project goes smoothly, she didn't have to listen to me crying for office when I had no idea what I was going to do. So thank you for your support. Thank you, Mr. Eisel, for being my physics teacher and making me realize that this field of study isn't just one which I had a passing interest in, but a real passion I wanted to pursue. And thank you, Mr. G, of course, for being by far the most involved and supportive teacher of my project. You advised me, guided me, and helped me in so many ways, not to mention allowing me into your classroom, and truly being the one responsible for making this project possible. Lastly, thank you, Mom, Dad, Emily, and Julia for being my family, paying for my courses, offering guidance when I needed it, and showing up for every event, including this one. Couldn't have done it otherwise. And finally, thank you all for coming and being such a great audience. Your support is appreciated. So with that, I'll open up the floor to questions. Yes?
Is there a reason why you chose to do problems on a ramp instead of on a flat plane?
Yeah, I suppose, so the question was, is there a reason why I chose to do problems on a ramp rather than a flat plane? To my answer to that would be that number one, ramp motion is slightly more complicated than motion on a flat plane, but also because I wanted to highlight the kind of parallelisms that exist between Python and physics, especially how I mentioned earlier that you have to divide a problem up into two parts when it's on the ramp versus when it's off the ramp. And so I just wanted to really show what Python was capable of doing and where you could use it.
Are you planning to continue in this field?
So the question was, am I planning to continue in this field? And I suppose my answer to that would be, as a current, yes. I do want to pursue a degree in physics, and depending on how things go in college, I think I would like to have a major in physics with a focus on particle physics and things such as the Standard Model. Yes?
I've heard the word Python a lot in this. What exactly is that?
So Python, the question was, what exactly is Python? Python is a coding language, and there are many different coding languages which are ways of telling the computer what you want it to do. Each coding language has a different paradigm, which is how the coding language is understood and read by the computer. Python is the coding language which is read in object-oriented paradigm, which means that data is grouped into objects, and each object has methods which determine what you can do with that object.
Okay, thank you.
Mm-hmm. Yes?
Do you feel like other coding languages would be better or worse version using this language?
Yeah, so the question, that's actually a really good question. The question was, do I feel that other coding languages would be better or worse for this field? I will say I haven't particularly done research into other coding languages at this present time. However, as I understand it, one of the main reasons why Python is kind of the industry standard is because it was originally created with the purpose of being able to be easily understood and read. And so for that reason, it allows you to follow the train of logic a lot better. However, I do know just kind of from hearing by and passing that C# is growing as a very important language in the field, especially in higher level physics due to its use in things such as linear algebra, which become necessary when you get into like college level physics. Yes?
How long did it take you to learn Python?
That's a very good question. So the question was, how long did it take me to learn Python? I will say I don't think I've learned Python yet. There's still so much I don't know and that I need to look into. And I don't know if you can ever really say that you've learned Python more than you can say you've learned a language. However, how much time I spent? I spent, I think, 70 to 80 hours learning the language over about 4 months' time, and that taught me what I needed to know. Yes?
May I ask, what exactly is particle physics and why do you want to major in it?
It's a very good question. The question was, what exactly is particle physics and why do I want to major in it? Particle physics is the field of study which focuses on the fundamental particles and the standard model. The standard model is basically a way of describing all of the different subatomic particles that are fundamental, which means they cannot be further subdivided. So electrons, for example, are an example of a fundamental particle. Photons are a fundamental particle, and quarks, which make neutrons and protons, are also fundamental particles. So it's the study of basically the most fundamental and simplest division of matter. And the reason why I want to pursue it is simply, I would say, because I find it interesting and I think it's kind of the way forward for gaining a deeper understanding as a whole into physics.
Time for one more question.
Yes?
After your project, what are your thoughts on coding? Do you like it?
That's a very good question. So the question was, after finishing my project, what are my thoughts on coding? I understand that the asker of this question asked this question because she does not like coding. I would say that I actually do quite enjoy it. It can be frustrating at times. However, I find that the end experience is very rewarding. And I mean, speaking personally, I've begun using Python outside of just applications in physics. Like I've used it for game design and just other things that I want to do in my daily life as well. So I really enjoy it.
Gabe, I appreciate you for trusting me when I said, oh, it's okay, we're gonna figure things out as we go, because you did a really wonderful job doing just that. Please, thank you today.
press the